That would take some digging. Okay, so we are finally getting into some real-ish, real calculus. Not that the other stuff wasn't real calculus, but this is the core of what makes calculus calculus. That was the background to calculus. Literally, it is what is going on in the background of calculus. So we're going to talk about differentiation with everything, and let's go differentiation. So we're going to talk first about the derivative and the tangent line problem. So we introduced the tangent line problem at the very beginning of the course, right? And we talked about it as if we were talking about a secant line that has two intersection points, and we bring them closer and closer together, so that average rate of change as the distance between those 2 points decreases to approaching 0 becomes instantaneous rate of change. Okay? So that's where we're headed with this. So calculus grew out of 4 major problems that European mathematicians were working on during the 17th century. Okay, so these guys were like in this big math club, and they were just like trying to all solve some of these problems. So the tangent line problem was one of them. Another one was the velocity and acceleration problem, minimum and maximum problems, and then area problems. So each of these involves limits and what happens as the definition of close comes into play.
How did they do this stuff? Like a calculator?
Do you know why this is called calculus?
No.
Because they didn't have a calculator.
How were they able to solve?
No, that was the problem. They couldn't. And so they had to find a way to condense all of these problems and to prove that it was the correct answer. So to condense all these hundreds of calculations, thousands, you could even say millions of calculations for one question to be answered down to a single problem that was easily done.
So they basically knew they were right. It was just a matter of proving it.
Right. So, well, first of all, they had to figure out what they were trying to prove. Then, okay, now we think this is the right answer. So now can we prove it mathematically? And can we get everybody to agree that this is logical and we've left nothing out? So they had to do peer review, things like that. So anything that's involved like in the research process and stuff like that for peer review, that has to be done with proofs as well. Okay? It's not like you can just say, hey, I'm gonna write this proof. You know, anybody watch Big Bang Theory? I like binge watched that show. I'd never seen it before until quarantine. So I binge watched Big Bang Theory. I identify with way too many characters in there. Anyways, wow. Hair has been broken forever. It just needs a couple extra screws, and I don't care enough to fix it. So, yeah, when Leonard and Sheldon, you know, they were trying to do different projects, and one time Sheldon did this thing, and he published it, and everything out was great, and it was on the radio, and everybody was like, yay, Sheldon, you did this, you solved this problem, and then he found a math error, right? And remember, I don't know if you guys remember that episode.
He said it to Stephen Hawking.
Yeah.
And he's like, there's an error, and I said it to Stephen Hawking.
Yeah.
He was, like, calling Stephen Hawking, didn't you show up to this house?
Yeah.
Yep.
Yeah.
Hey, man.
I love it that show has like all these special guests, and like Stephen Hawking actually was on that show, you know.
I wrote a report on Stephen Hawking's life.
Mhm.
He is my hero.
I like the movie about him too. That's pretty good.
Yeah.
Anyway, so back to calculus as we digress. So the tangent line problem. So we talked about this. What does it mean to say that a line is tangent to a curve at a point? Okay, so what we mean is that line intersects the point at that curve at only one point. So the line intersects the curve at only one point. Okay, and we approximate this using a secant line. okay, through the point that we're trying to prove its tangent at, this one right here, and a second point. And then we gradually decrease the distance between the points by bringing the second point closer and closer to the first point, so that eventually this delta x approaches 0. When that happens, we are approximating the instantaneous rate of change. But with calculus, we can show we are actually calculating the instantaneous rate of change, not just approximating it. Okay? So, this point C comma f of C is the point of tangency, and C plus delta x comma f of C plus delta x is a second point. And if we want to find the slope of the line through those 2 points, we use our handy dandy little slope formula, which is change in y over change in x. So I'm going to label these. This is x1, y1, x2, y2.
Why can't we just say that? Why the C, the delta X?
Because we're trying to generalize this for every single point on every single curve. So that's why we don't say, hey, it's a specific function. We say for any function f. That's why we don't say, hey, only when f of c is at 2 and that delta x is 0.05, right? We have to generalize it for any value of c along that x-axis and any delta x away from that c. And so by using variables in our proofs, we have now generalized this so that it applies to everything. Okay? Does that make sense to everybody? Now, it looks crazy, and you're like, where did all the numbers in math go? Okay? Now, remember I said algebra was snapshot math, right? If I were to put numbers in here, that's snapshot math. That's math at a particular instance. I need it to cover anything. So this is movie math, right? So the right-hand side of the equation is a difference quotient. Okay, we talked about that. It's called the difference quotient, DQ, not Dairy Queen. Okay? I need a blizzard. Okay.
I was mumbling, I want Dairy Queen.
Yeah, or a dipped cone, or, okay, I'll stop. Okay. Okay, so the definition of the tangent line with slope m. So the limit as that delta x approaches 0. So as we get closer and closer between the point of tangency and the second point of our secant line, as that distance approaches 0, because we're bringing them closer together, okay, we are trying to find out what's happening to our delta y and our delta x, right? Well, what it turns out is, as delta x approaches 0, the limit of delta y over delta x as delta x approaches 0 is actually equal to the slope at x comma f of c. Okay, and where m is the slope of the tangent line to the graph of f at the point comma c comma f of c. Okay. Now, that has several meanings in real life. Okay, I'll let you guys copy this first and I'll take a sip of my beverage. This is how much I like teaching calculus. I didn't just give up and go home. Thank you so much, Taylor. You rescued the night because I was getting really frustrated. And then I had this thought, wait, but there's a second way to connect. I wonder. That's what life is. You know, you get thrown some obstacle and you're just like, okay, how am I going to get around it?
My favorite idol says, just keep on keeping on.
Yep. Okay. So to find the slope of the graph of f of x equals 2x minus 3 when c equals 2. Here's what we're going to do. First of all, we're going to open Desmos because Desmos is my friend. Desmos rocks. Oh my gosh, yes.
Definitely don't know the best.
You're welcome. It was x equals, or c equals what? I can't remember anything. 2. I'm going to make it x equals 2 so you can see where this point is, right? It's the point 2 comma 1, right? Okay, that's the y value through that, okay? Why did we do that? Because we didn't feel like plugging into and solving for y, but, you know, whatever. Okay, so looking at this, I'm going to erase some of this because, oh, not that color, H, this color. Okay, so we plug all of this into our handy dandy little formula. Yes, that is a Blue's Clues reference. Okay, so here we have our y2 minus y1 over x2 minus x1, right? Only because we don't know what delta x is, okay, it's going to stay how it is. So we're going to have f of 2 plus delta x minus f of 2 over delta x, okay? So how do I find f of 2 plus delta x? Well, that's going to be 2 times 2 plus delta x minus 3. That is the quantity f of 2 plus delta x, okay?
Where did the 2 plus delta x come from?
No, I understand where that comes from. Look at the 2 on the c equals 2. Is that what the 2 goes?
Yeah, okay, let's remember the formula. Okay, hold on. We're all good here. We're all good. We're good. We're good. It's this formula right here. This is why we should always write formulas before we start working. Okay, so there's the formula, okay? So f of what was c? 2 plus delta x minus f of what was c? 2 over delta x, right? So we're just going to keep this as delta x.
Okay.
Now this minus is that minus right there, minus f of 2. So that's going to be 2 times 2 minus 3. Okay?
The 3 is this.
Yeah.
So the c goes where the 2 is, right? And then the f of x goes and encompasses.
Okay, see where x is in there in 2x minus 3? In the first one, in this one, in place of that x, we put 2 plus delta x. In the second one, we're just placing 2. I guess I should have written it like that. Yeah. Missed a set of parentheses, confused everyone.
They're like calculators.
Because it completely changes the value. Okay, so now what we can do is distribute. So 2 times 2 is 4. 2 times delta x is 2 delta x minus 3. Minus 4 minus 3 is 1. I don't need parentheses. I don't need parentheses over delta x, right? 4 minus 3 minus 1 is 0. So this becomes 2 delta x over delta x, which is just 2.
I was trying to look over this weekend now to try to get a jump start.
Yeah, now you see it? Yeah. Now, That is when you know what C is, okay? What if we did not know what C is? What if the problem instead was for any value of C? Or it didn't specify a value of C. How would I solve the problem then? Well, I'm just going to have, at any value of X, I would let C equal X, and I would just say, so I would have, sorry, I didn't, hold on a second. Hold on one second. Oh, stop that. Okay. I can't erase when I do this. I forgot to take my limit. So now I take the limit as delta X approaches 0 of 2, which is 2. Now I finish. Sorry, I realized I hadn't taken the limit. So now for any value of C, we'll let C equal X, and I'll have the limit as delta X approaches 0 of f of X plus delta X minus f of X over delta X. This is usually how I'm used to seeing a difference quotient, okay? And I will actually plug X plus delta X in to my original formula, which was 2X minus 3. So I will have the limit as delta X approaches 0 of 2 times X plus delta X minus 3 minus the quantity 2X minus 3 all over delta X. It's good. You're gonna get the same thing, hold on. Okay, so that will equal the limit as delta X approaches 0 of 2X plus 2 delta X minus 3 minus 2X plus 3 all over delta X. Now, when you're doing it for any value of C, which is usually how you're used to calculating difference quotients, remember, anything without a delta X has to disappear, right? Yes?
Sorry to go back, but why do we keep putting the 2 in for that?
The original function had a 2. So when my f of X is 2X minus 3, I have a structure that I'm working with. I have a 2, I have an input minus 3. Okay, that's all right. This is what these are questions you guys need to ask to make sure that I don't like leave you in the dust. And that was a very insightful question. So, okay, so now 2X and negative 2X 0 out, negative 3, positive 3 0 out, and hey, I'm just left with 2X over delta X again, right? So that's equal to the limit as delta X approaches 0 of 2 delta X over delta X, which gets me back to the limit as delta X approaches 0 of 2, which is 2. Well, so you're like, well, yo, I got the same answer, yes. Now, what was the slope of the line 2X minus 3? 2, right? So if I'm asking for the tangent line to a curve and that curve happens to be a line, the tangent line to the line is going to actually be the line itself, right? Because all I'm finding is the slope of that line, right? Now it's not actually a tangent line to a line because it intersects at infinitely many points, but you get the point, right? If that original line had been a curve, I would have had the instantaneous rate of change. But because it's a line to begin with, the instantaneous rate of change is equal to the average rate of change, which is equal to the slope of the line, okay? And that's what this slide is saying. So the definition of the tangent line to a curve does not cover the possibility of a vertical tangent line. Okay? For vertical tangent lines, we can use the following definition. If f is continuous at C, oops, hold on, and the limit of the difference quotient as delta x approaches 0 is equal to infinity or negative infinity, then the vertical line x equals c passing through that point is a vertical tangent line to the graph of f. So if you take your limit and you end up with negative or positive infinity, you know that what you tried to take the limit of was a vertical line. Make sense? And by all means, if I say makes sense and you say, yeah, right, let me know, please. I'll find another way to explain it.
So,
Mhm.
back to the difference quotient.
Mhm.
So, the parentheses c plus delta x, that is what we were plugging in
Instead of x,
instead of x.
for every x in your function.
And then the brackets are the function itself.
The brackets. Oh, okay, that just separated that value of f of c plus delta x.
Right, so that's our function,
That's-
that's our function, and that's our function we're in. And that's what we're plugging in for x.
That is saying, hold on, I'm gonna add a, okay. So let's break this down. So we had f of x equal to 2x minus 3. We had a couple quantities we needed to find. We need to find a f of x plus delta x. We needed to find f of x, right? Then we needed to subtract the 2. So we have 2, and then we have an input for x minus 3. What goes in that input? X plus delta x. Okay?
So we're just plugging that
Just
in.
plug it in. Whatever's in the parentheses goes in place of x. In place of every single x you've got.
So if, let's say x squared minus 3,
Right.
you just put a square root on it.
It would be x plus delta x squared minus 3. Okay?
Then the c thing
That makes significantly more sense.
Yes. And then we've got just f of x is just 2x minus 3, right? And the difference quotient says I need to take this quantity here minus this quantity here, right?
So we're just gonna subtract whatever that from that.
Right. All over delta x, right?
Let's take a picture of this.
That's why it's here. So then that just equals this. And then the minus, right? And that minus, I'm going to put this in a different color, is this minus right here. Okay? We getting it now? And I'm going to put parentheses around this so that we distribute that negative.
So it took me a second.
when the C came in, you just plug it in for the regular X.
Right, right. Because I'm using it for any value. See, C is an X value, right? I'm just gonna let it equal any X value. Okay?
And then, so what if like the delta X don't get canceled out?
You did something wrong. No, I say that wrong. The delta X's shouldn't cancel out. Everything except the delta X's should cancel out, or you did something wrong.
So say if
you have
add a delta X in it, you did something wrong?
No. If you have like a -3 left over, you did something wrong. It should have canceled somewhere. Okay?
And then in our answer before, it was just 2.
Okay, that's when you simplify, right? So you have this plug and chug step here, right? Once you distribute and combine terms, the only thing that should be left are stuff with delta X's.
So
Okay.
basically before you solve.
Right.
So
Before
basically
you-
2 delta X.
yeah.
Delta X.
It'll make more sense when I do a more complicated problem, believe it or not. Okay.
And for what you were saying just a second ago.
I know that doesn't make much sense, but sometimes a more complicated problem is better. So, for example, the function shown in figure 2.7 has a vertical tangent line at this value of X equals C, right? Okay. So if you went to go find the limit as delta X approaches 0 of this difference quotient for a C value at this particular C value, you would get that the limit was equal to either positive or negative infinity, right? And that means that there's a vertical tangent line through the curve at that point. Okay?
The point of where you're trying to find the limit.
Right. Okay? I could show you a problem with that there, but suffice it to say that if we were actually looking at this, it would be like a cube root problem.
I mean, but this.
And I don't think we want to do that right now.
That's okay.
Let's stick with some nicer
It
polynomials.
just changes as long as it's vertical. It's if it's infinite, it's a vertical tangent line.
Right. Now we'll talk about what that means in terms of derivatives in a bit. Okay, so when the domain of F is the closed interval from A to B, you can extend the definition of a vertical tangent line to include the endpoints by considering continuity and limits from the right for X equals A and limits from the left as X equals B. Okay, so remember what that meant. Okay, so say we had this problem and the function was, I'm going to draw a semicircle here. Just this is supposed to be so here is A, here is B. This is the domain of the entire function, right? Okay. If we wanted to find the tangent line to the curve at either A or B, do you all agree that it would end up being a vertical tangent line?
Yeah.
Yes. That makes sense, right? Okay. And by tangent line, I literally mean that if I were finding it at a point like right here, okay, imagine that this point, you've got some sort of line that extends down to the origin. Okay, imagine that's to the origin. There we go. Okay, and that literally, whoops, that literally is tangent to that line that intersects the, and it's only the origin because that's the center of rotation for that particular thing, right? If it was a little bit more irregular, you would have that center of rotation for the curve be somewhere else, but you kind of get the point, you know. I wish I could do it so that all the Zoom people could see, but I typically will show tangent lines with a pencil, you know, and you can kind of imagine that there's a tangent line or a perpendicular line to the tangent that will point to some point inside that curve that's at the middle of the section where it's concave either up or down, right? Okay, so if it had a centroid, that's where that perpendicular line would pass through. Does that make sense? I'm not saying that it does have a centroid, I'm just saying if you could imagine that, that's kind of what we're talking about. Okay? At least that's how it's always played through in my brain, for what it's worth. Okay, so the derivative of function. So the limit used to define the slope of a tangent line is also used to define one of the two fundamental operations in calculus, which is called differentiation. And we define the derivative of this function at x as f prime of x, which is the slope of the tangent line to that curve at a particular value of x, as equal to the limit as x approaches 0 of the difference quotient for that function, provided the limit exists. Okay, so for all x for which this limit exists, f prime is a function of x. Now, that's some notation. So this f prime then is what we call a derivative. It is one of the many notations for derivative. We'll cover some of them a little later. Actually, probably the next slide. But in the math wars, as I refer to them, which was the general math arms race in the 1700s to maybe early 1800s for the study of calculus. Okay, we had lots of guys that were really vying to have their versions be the one that was accepted worldwide. The problem is like any complex problem, there's lots of different ways to look at things, and some of them have valuable insights that others don't have. So none of the notations has really died out. They're just all useful for different ways of looking at the problem. Okay?
So what's the F prime for? Like, why is it prime?
F prime? Because it's F prime. In section 3, I believe it is, we'll cover how you can have other things instead of F prime, like F double prime and F triple prime.
Wouldn't that just be
Your answer. I can't hear you. Just flow with me for a sec, okay? You're trying to put it all together in your brain, and you don't know enough to put much together with. Because I haven't had a chance to talk about it yet. So, now, we talked about the slope of that tangent line through a point being equal to instantaneous rate of change, right? Okay. So the derivative is related to instantaneous rate of change. So what we're finding then is a function that will allow us to calculate the instantaneous rate of change for any point along the original function's domain. Now, with our line 2x minus 3 being the original function, we got the derivative equals 2, right? Was that the instantaneous rate of change along any x in that function? Yes. Now, say instead of 2x minus 3, it was 2x squared minus 3. Would we have gotten 2? No, because we know that's a curve, not a straight line. So we would have a function, one single function, that allows us to calculate the instantaneous rate of change along any point on a parabola. That's why calculus is powerful. Okay. So the derivative can be used to determine instantaneous rate of change. Okay? And the process of finding the derivative is called differentiation. Now, this last paragraph here talks about how we conjugate this word and use it in different tenses, I should say. So a function is said to be differentiable at x when its derivative exists at x and is also differentiable on an open interval from a to b when it is differentiable at every point in that interval. So what do I mean by differentiable? That means I can calculate a function, right? Can I calculate a function if the limit of that difference quotient is infinity or negative infinity? No. So would it be differentiable at a point like that? No, right? So I'm looking for a function to define the instantaneous rate of change along any point on my original function, right? And if I can't find a function, then I can't, at a particular value of x, then my original function is not differentiable at that value of x, right?
Or y was not differentiable.
No, we found a function. The function was a constant function, too.
Oh, okay. So,
Okay, but I was saying, like on that cube root function, right? At any point, if you have a place where you do that limit as x approaches, you know, and my c value is that particular point that causes a vertical tangent line, you don't get a function, you get a infinity or negative infinity, right?
basically, it's just it's to find the slope at just that point, right?
It's a function defining, a function finding the rate of change of a function.
Right. Yes, thank you, Taylor.
So if something.
Did everybody in Zoom land hear that? He said it's a function defining the rate of change of the original function. Okay?
So if the original function has a vertical tangent line, then you can't do it for the whole thing.
If it has a vertical tangent line, then the derivative's function will not be continuous,
Okay.
because that derivative would then have a vertical asymptote.
Okay.
Got it? Okay. Very good questions tonight, guys. Ooh, loving it. And Zoomland people, feel free to chime in with questions too, okay? Okay, so in addition to f prime of x, there's other notations. dy dx, dy over dx, we call this dy dx, is Leibniz notation, if I'm not mistaken. I don't think this book talks about it, but, and then we have y prime, so in place of f of x, you know, because y equals f of x, they're like used interchangeably, right? So sometimes they use y prime. Sometimes they talk about the derivative with respect to x of a certain function, f of x. And sometimes they do the same thing with this d sub x of y. Okay, so if you're bored or really trying to figure out something weird in math, take time to visit Google Books. Okay? Let me show you what I mean by Google Books. I don't know if you guys knew, not giggle or whatever I tried to put there. Oh my gosh.
Start going on with it.
There you go.
Okay, I'm having problems with the, because the closer I get to my screen, the more reflection I get off the lines, and so I can't read what I'm writing. It's not that I am blind, but anyway, so Google Books is this wonderful thing, and I'm going to type in calculus book. And what you're going to get is gobs and gobs of calculus books from all over the world. And you're going to find that the higher you get in math, the more varied the notation is. Okay? Because, I don't know, I think everybody thinks they've got the best things, sliced bread, and, you know, so that's why, really. Okay? So you'll run into these things, and we introduce them to you because if you're like looking at different books, let's see if I can find like a really weird one. We'll go here.
Calculus for dummies.
Yeah.
Oh my god, that one.
I think I need that book.
There we go.
Calculus for people who are whiny and fussy and cry when they look at calculus.
I say something from India because math is truly like a universal language, and so a lot of math books written in India are written in English. But let's see if I can find some of their. See? Important limits. See how they use weird notation? See? Those are their derivatives. Okay?
Is that a pitchfork?
See what I'm talking about? So,
So I'm a liberal snowflake, but
So-
I'm very glad to live in America right
you
now.
know,
Because
yeah. So, I mean, but it's nothing different than what we're doing right now. It's a calculus 1. It just is a different notation. That's what I mean by it. Okay? So we introduce you to some of these notations so that, say you go meandering around, you're not going to be entirely lost. Okay?
Yes, I'm just gonna do India to do calculus.
You never know where you're going to end up. I'm just saying, we try to give you as many clues to the road maps as possible. And you may not enjoy it, but tough. Okay. Okay, so all of these notations are the same thing. They're all derivative notations. Any of these means take the derivative with respect to x. Okay? So now we're going to do a different one. Hold on. Whoa, 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 whoa. You can't look at that yet. Sorry. That's more than your brains can handle for one.
that's an understatement.
Okay. Not trying to insult you, just saying that this is why I erase it.
You're right.
Oh gosh, my glasses keep fogging up and I can't see. Okay, so we're going to use this definition of a derivative to find the function that is the instantaneous rate of change of x cubed plus 2x. Okay, so we're going to go up here. We're going to find the little formula again because we don't like not having our formula. In reality, you would write this down. Why would you write this down? Bingo. Okay, so there's my formula. Okay, here's my function. Okay, so let's start plugging and chugging, right? Does everybody know what plug and chug is? Substitute and evaluate. Okay, equals the limit as delta x approaches 0. Okay, of f plus delta x. That means in every x in this expression, we are going to put x plus delta x, right? So that whole expression will look like x plus delta x cubed plus 2 x plus delta x. Okay? Then the minus comes from the formula. All of f of x, which is x cubed plus 2x. And that all goes over delta x. I'm separating off a little thing because we have some calculations to do. Specifically, we need to calculate out what is x plus delta x cubed. Huh?
Because my x minus delta x on the outside. And then x
No, you're thinking sum and difference of cubes. I'm actually taking x plus delta x times itself 3 times.
Yeah.
Okay? Did anybody remember Pascal's triangle?
What? I've never even heard of that.
Okay.
I've always just been told to do the square.
I'm so sorry. I'm going to show you the shortcut. Are you good with the shortcut?
Yes.
Okay.
Always love
So we're going to take a little detour into Pascal's triangle. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, 1, 7, 21, 35, 35, 21, 7, 1. Are you seeing the pattern?
So whatever
Yeah.
whatever Q is,
Right? Okay. So I want you to think of it as this is 0 degree. This line here is 1st degree. This line here is 2nd degree. 3rd degree. Oh, hey, do you notice that these numbers here match these numbers along that, right? Or the other way, right? Okay. So say I had x plus 1 to the 0 power. What would that be equal to? Anything to the 0 power is 1. What is x plus 1 to the 1st power? X plus 1. What is x plus 1 to the 2nd power? What is x plus 1 to the 3rd power? What's x plus 1 to the 4th power?
Wait a minute. Hold up. I feel cheated.
I am so sorry that that you missed out on the fun that is Pascal's triangle, but hey, here you go. So now, okay, so the coefficients, right? Okay, so say we have, we're gonna do this, okay, I gotta show you this for a minute. We're gonna use 2x minus 3. I'm gonna take 2x minus 3 to the 2nd power, right? Okay, so I have the 1st term and the 2nd term. I'm gonna have a and b. I'm gonna call it a and b, right? So this will equal a squared plus 2ab plus 1b squared, right? Now what is a? 2x plus 2 times 2x times negative 3 plus negative 3 squared, right? So this ends up being 4x squared. 2 times 2 is 4 times negative 3 is negative 12x plus 9.
this is worth the tuition right here.
So if I needed 2x minus 3 to the 3rd power, it would be, this is my a, this is my b, right? It is going to be a cubed plus 2a squared b, or sorry, 3rd power, 3. plus 3ab squared plus b cubed. See how the a's decrease in power and the b's increase? And the total powers always equal 3, right? So a cubed, and this is, sorry, this is really like saying b to the 0, right? And a to the 0, okay? So if you add the powers up, they're always going to equal what the power you're raising it to.
This all works on binomials.
What now?
Only works on binomials?
Yes. Okay. But all you need it for is binomials. And for like the next 45 minutes. Or today. Okay. Well, this week. End. Okay, so now you see where I'm going with this, right? Okay. So when I need to raise x plus delta x to the third power, okay, it is going to be x cubed plus x squared delta x, right? Plus x delta x squared plus delta x cubed. You with me on this? Because if I would have just done that,
So and X is.
oh,
power.
3.
Yeah.
Forgot my 3s. 1, 3, 3, 1, right?
X's go left to right and decrease.
Mhm.
X right to left.
Mm-hmm.
If you don't have the same powers.
Right. So that was what I needed. Sorry, I had to take that little detour, but that is the value of this term just right here.
Any other shortcuts?
I'm working on it. I remember being taught Pascal's triangle, and it was the most exhilarating
No, they were just
thing.
like, do the square.
No, that's mean. But then I was part of a high school that we actually had a competitive math team.
So Pascal's triangle would have been great.
Oh, that was easy stuff compared to the stuff that we did. Like, okay, there's a group called mu alpha theta.
What?
Mu alpha, M-A, theta, T-H, math.
Oh.
Anyways, they have competitive math, like, competitions all over the country. Like, and in Florida where I grew up, like I was in Hillsborough County in Tampa. I grew up in Tampa. And we would compete, the high schools, my high school with all these other different high schools, and we would have, like, it was a nerd convention. It was so wonderful. And then we would have statewide nerd conventions. And we actually had dances and stuff like that. Nobody danced. They were all nerds. How do you tell an extroverted engineer from an introverted engineer? No, they look at your shoes, not their own.
After not doing so hot by my standards in geometry, I never joined.
Oh.
In middle school, I was part of that.
Now, I'm not saying I did well at these competitions. I just was interested enough to try to do them.
They were just like, you know what, you're one of the smart kids in this school.
Yeah.
Join?
I
Sure.
felt like a tag along next to all these math giants.
So you put a math question on the board and you're like,
No, you'd get a test, okay? You get a test, and you'd get in a room, and you'd have your own little desk, and it'd be timed. And you had to see how much you could do before time ran out. And they timed your test, and then your score, and they combined that all into a score, and they would take everybody's from the whole team, and that would contribute to your team score.
Huh. Okay.
Yes.
In middle school, they would just give you a problem.
That'll cure test anxiety. Yeah, but anyway, so that was how this worked. And it was, you know, it was stressful, but really good for me to get creative with math and feel comfortable with getting creative.
Somehow Kansas gets more whack. You don't ever hear anything.
No, you don't. And I had thought when I got into teaching that I would find more of it. Okay, so I'm finishing up this problem, minus x cubed plus 2x. Okay? All over delta x. So I just distributed this, distributed that, and that's how I got my last 4 terms. Now, let's look at what I've got. Okay? So my 2x, oh, sorry, and a negative, oh, shoot. Okay, there's a way to do this. Minus 2x all over delta x. Okay, so 2x and negative 2x, right? X cubed and negative x cubed, and everything else has a delta x in it, doesn't it? So I'm good. So the limit of this as delta x approaches 0, and I've got 3x squared delta x plus 3x, sorry, delta x squared plus delta x cubed plus 2 delta x all over delta x. So I'm going to factor a delta x out of everything on the top. Okay? GCF factorization. This is why we teach it. Why? It's a skill in calculus. So I'm going to have 3x squared plus 3x. I lose a delta x out of the delta x squared, and I have 1 left. I lose a delta x out of the delta x cubed, and I have 2 left, plus 2 all over delta x. Slash, slash. So now I'm finding the limit as delta x approaches 0 of 3x squared plus 3x, oops, delta x plus delta x squared plus 2 as delta x approaches 0. So how do I find this limit as delta x approaches 0? Substitute 0 for delta x. So that equals 3x squared plus 3x times 0 plus 0 squared plus 2. So that ends up being and that gives me 3x squared plus 2. Now, what do you notice about the original function and my derivative? You bring down the power and then decrease the power by 1 because this is really x to the 0. So there's a shortcut even.
Is that applicable to all of them?
Bingo. Yes. We just have to torture you with the difference quotient to make you appreciate it. No, don't tear that out.
I had it written on the other one and I was just working on long
Okay,
ones because I
okay.
ran out of room.
Okay. I thought you were frustrated with your notes. Because I haven't tortured you yet enough, you know? No. Okay, good.
It does.
Zoomland people, are you all good with this?
Yeah.
Yes.
Now we know where.
Good, thank
Yeah.
you. Okay, everybody good with Pascal's triangle and how that can help you? Where'd you go to school? Who's your teacher? Name one.
I had Jane Cleve for pre-calc trig, and then Grant Staff for honors university.
I don't know any.
I went to the news and I had Morosky with them on Facebook and I'm going to message her.
When did you graduate?
Huh?
When did you graduate?
This year.
Oh, okay. I know a teacher who used to teach there, but she's in charge of math for the whole district now. Okay, so differentiability versus, wait, hold on. No, we're going to do example 4. We're going to do example 4 because example 4 is going to help you with the algebra portion of all of this. Okay? The algebra portion. Okay, so here my f of x equals the square root of x. Okay? And first of all, we are going to find the derivative, and then we'll find the slope of the graph at points 1, 1, and 4, 2, and we'll discuss the behavior of the function at 0, 0. But first, I just want to find f prime, right?
Yes, it's huge. Yeah.
Okay?
Okay.
So, going and grabbing my little function card here. My formula. There's my handy dandy little formula. Okay.
When you're so like the derivative of bringing out how you use for the square root so that 1/2 is one thing.
That's why I'm showing it to you. It would be nice if it did, but it doesn't. There's another trick that happens in these, and that's why I'm making sure to show it to you. Okay? Okay, so f prime of x will equal the limit as delta x approaches 0 of f of x plus delta x. So this is going to end up being the square root of x plus delta x minus f of x, which is just the square root of x, all over delta x. Now, that looks really nice and easy.
It's not.
It's not. What happens when you plug in delta x equals 0?
You can't divide by 0.
You end up with 0 over 0, which is indeterminate, which you can't do. So you've got to do that square root funky thing, right? Where you multiply by the conjugate over itself. Okay.
Basically, our whole numerator, but plus instead of minus.
Yes, the whole numerator, x plus delta x, but instead of the minus, there's a plus. All over excuse me. Well, I think there was a plague going on or something that kept him quarantined.
Seems very familiar in some way.
Just saying, lots of good things happen in quarantine.
Maybe.
Okay.
Unless you're an essential worker, in which case you're getting exposed.
People on Netflix might think I'm going to go through this.
Yes, I'm bitter.
Socrates is in front of us. Let's go.
Yes, the story goes that calculus was invented because the bubonic plague, indeed the Great Plague of 1664 to 1665, closed Cambridge and led Isaac Newton to retire to meditate. As a result, he invented calculus.
Let's think numbers.
So that you can relate, yes, that is why we have this, but it beats the alternative. Okay, so now think of this as binomial times binomial, but these are special binomials because they are conjugates. So when I take the inners times the outers, what's going to happen? They cancel each other out. So it ends up being just first times first, last times last. Now I can say this because we've talked through the reasoning. A lot of people will give me two binomials and just take the first times the first and the last times the last, but they're not conjugates, and that's wrong, right? Okay, so what is the square root of x plus delta x times itself? Right, it's just going to be x plus delta x. No, that's this times this, right? And then negative square root of x times positive square root of x is just going to be negative x all over Now I've got to take square or delta x times each of these, right?
Maybe just put delta x in front of it.
Right. Okay. So combining like terms, I just get delta x on top, right? And delta x times the square root of x plus delta x times the square root of x. Now, am I good to just substitute delta x? No. But if I had not multiplied this, it would have been actually better. Because then I could take delta x times square root of x plus delta x plus square root of x, sorry. And then that cancels out. So had I not distributed the bottom, I would have been better off. So this just becomes the limit as delta x approaches 0. See, sometimes you make a mistake, but it's salvageable, right? Like, oh, yeah, I wasted a step, but it's not the end of the world. I see it now. So we have the square root of x plus delta x plus the square root of x. Now can I substitute x in? Equals 0, right? I can. So that's going to be the limit. Sorry, when I substitute 0 for delta x, that's taking the limit. So I no longer need to write limit stuff. So that's going to be 1 over the square root of x plus 0 plus the square root of x, right? Which is 1 over the square root of x plus the square root of x, which is 1 over, how many square roots of x do I have? 2 square root of x. A lot of people have a hard time getting from this to that. It wouldn't let me highlight because I had already written. Okay? Yes.
The one where you have the x plus delta x minus x in the numerator.
Okay, which line are you on? On my screen. I've got the line with the pink, the line underneath that.
It's like right underneath the pink.
Right underneath, like right in here?
Yeah, it's the one right underneath the pink. So
It's
after
the
you
second.
This one?
yes.
Okay.
Yes. Okay. So I know the delta x is canceled, but you have x.
Only
The x and the negative x cancel. They zero out.
Oh,
Cancel is top to bottom. Zeroing out is side to side.
okay. So that's why it would equal 1 because those are top and bottom.
Okay.
I see.
You got it now?
Yeah, got it.
That's an excellent example of following along. And when you lose me, because you are following along, you can ask a question to get yourself found again. Yes.
Wouldn't you have to multiply by the conjugates again because we have square root of the or
Okay. You missed that part of my rant. So why do we rationalize denominators? Who remembers that part of my rant?
That was an American thing, right?
Yeah, it's the American thing. Why did we do it in America?
We don't like crap.
Well, why did we start doing it to begin with? Slide rules. Slide rules. Computer, calculator, slide rule, calculus. Actually, logarithms, calculus. So, in the history of computation technology, that was counting backwards. Yeah, so there was a technology before actually having computers and calculators, okay? And it required ratios to approximate things. And so having irrational numbers in the denominator made the ratios difficult to calculate. So if they could have a rational number in the denominator, then it didn't matter so much that there was an irrational one in the numerator. Dividing by a rational number versus an irrational number was way easier because you could take a decimal divided by a whole number.
Okay, so you're not looking for those to do the,
No, I'm not. You can absolutely leave these in the denominator. Now, knowing how to write these in exponential form is good, right? Because in exponential form, this would be 1/2 x to the negative because it's on the bottom, 1/2 because it's square root. Okay? So knowing how to switch between those two forms is very necessary. We will do a lot of that. But, and it's also easier for seeing that, hey, my original function was f of x equals x to the 1/2, right? How do 1/2 and negative 1/2 relate to each other? The degree is decreased by 1. The difference between them is 1, right? So 1/2 minus 1 is negative 1/2, right?
just the same.
It's the same thing, right? So the 1/2 comes down in front, and the degree decreases by 1, which gives it a negative 1/2. See it?
Sorry for getting so lost.
No, don't be sorry.
So when we have the square root of x plus delta x, why does the delta x under the square root go away?
Because you factor.
Because we substituted delta x equals 0 to take the limit.
Oh, that's when we're substituting our
Correct.
equation. Okay.
That's why we stopped writing limit in front of everything.
Okay.
Well, except for this instance here, which was me just taking a shortcut and not writing limit. I should have wrote limit, but we're simplifying. So we're all good? Okay, relationship between differentiability and continuity. So we said that f prime at c is equal to the limit of f of x minus f of c over x minus c as x approaches c, provided this limit exists. We talked about what happens if we have that vertical tangent line, right? Which means the limit would not exist there, right? Okay. So, the existence of this limit requires that one-sided limits exist and are equal, right? So you have to take the limit from the left, the limit from the right. They both have to exist and they both have to equal each other, right? So these one-sided limits are called the derivatives from the left and the derivatives from the right. And so thus it follows that f is differentiable on the closed interval from a to b when, if it's differentiable on the open interval and the derivative from the right at a and from the left at b both exist, right? Does that make sense? So on the open interval, we just have to say that the derivative from the left and from the right is good and equal, right? They exist and they're equal. But if we want to do it on the closed interval, we have to do one-sided limits at a and at b, right? So at a, we're going to have to do the derivative from the left. At b, we're going to have to do the derivative from the right. And they both have to exist. They don't have to equal each other. They just have to exist. Okay? And then we could say that f is differentiable on the closed interval from a to b, not just the open interval. Okay? Everybody good at that? You understand what we're talking about? Okay, so when a function is not continuous at a particular value x equals c, it will not be differentiable at c. So think about our step functions. When we have a jump in a step function, the limit from the left did not equal the limit from the right. Therefore, it cannot be differentiable because differentiability implies that limits from the left and from the right exist and equal each other. Right? Are we good? So things that can cause the inability to differentiate at a particular number in my original function can look like jumps or discontinuities. Now, what kinds of discontinuities did we have? Removable and non-removable, right? What kind is a step function? Non-removable. I can't plug it with anything, right? Okay. Removable are just wholly functions, right? How many different types of those did we have? Well, we had plugged and unplugged, right? Plugged holes and unplugged holes, right? Or holes that we tried to plug, but we kind of missed, you know? Like, so there were 3 different things that could cause discontinuities. We could have just a flat out hole in the function. We could have a hole that's plugged somewhere else, and we could have a jump. Okay, 3 different things. Okay, so if any of those 3 things happen to cause a discontinuity in my original function, the places where they happen won't exist in my derivative function. Okay, they will not be in the domain of my derivative function. Is everybody good with that? Because if they were discontinuous and I couldn't get it to work, then it's not going to be in the domain of my derivative function. So it's not differentiable at those values. So we can observe this with our square root or our step function. Okay, and we're going to take the step function is not differentiable at x equals 0 because it's not continuous there. Okay, so when we take the limit as x approaches 0 from the left, we get that that is equal to positive infinity. The limit as x equals 0 approaches 0 from the right is equal to 0. Those 2 things are not the same. So therefore, it is not differentiable at x equals 0. Okay, so although it is true that differentiability implies continuity, the converse, that continuity implies differentiability, is not true. Okay, in order to have differentiated, we needed to have a continuous function, right? So if it's differentiable, it must have been continuous. Okay, but just because it's continuous does not mean it's differentiable. Those are more subsets. This is just converse. Conjecture, hypothesis, conclusion versus conclusion, hypothesis type thing. That's converse when you swap those 2 around. Okay, so now what types of functions would have continuity but not differentiability? Now, how do we not have differentiability? What's one of the rules we can break to not have differentiability? Hint.
What about sine and cosine functions?
So if the derivative from the left is not equal to the derivative from the right, even if the function is continuous, we wouldn't have differentiability, right? So think about what types of functions would have different derivatives on the left and the right, on either side of a value. Huh? Absolute value. Slope on one side, slope on the other side. Are those 2 slopes equal? No. One's negative, one's positive.
What about square root?
Yeah, that's fine. And it's only not differentiable at that vertex, right? It's differentiable everywhere else. So what does that vertex have, though? It's got a sharp point. It's not smooth. So sharp points are a problem for us in differentiability land. They're still continuous. It's just because the slopes are not equal on the left and the right at that vertex x value, then we have problems finding the derivative because the derivative is based on a limit.
So then would like inequality setups work? Like one equation is when x is less than one value?
No, because inequalities, if you have two variables in an inequality, have infinitely many values vertically, so they're not truly functions.
Okay.
Fair enough? That's why we shade them. Okay? So they act like functions to a point. No pun intended. They act like functions, but they're not really because each x has more than one y. In fact, it's got infinitely many of them. And that's why we show it with shading. Does that make sense to everybody? They're not truly functions. They operate a little like functions, but they're kind of off in their own little, they're relationships, okay? Remember, functions are a subset of relationships, math relations.
So like what's another type other than absolute value?
Absolute value is the main one. The pointy ones. I don't know of any other pointy function. Oh, I'll show you some more. There's a couple others. Any functions with a point, a sharp turn. Okay? So here's the absolute value of x minus 2, right? It would not be differentiable at x equals 2 because the slope on the left side is -1. The slope on the right side is +1. So as we take the limit as x approaches 2, right? Okay, the limit from the left is going to be -1. The limit from the right is going to be +1. Those two don't equal each other. So it is not differentiable at x equals 2. Is everybody good with that?
Like at that point, when the two lines are coming, they're going to be, if the slopes aren't the same, it's not differentiable. Okay.
And when the slopes aren't the same, you're going to see it has a sharp point to it. Now, the sharp point could be caused by lines, it could be caused by curves, but it's going to be a sharp point. And a lot of times it has to do with absolute values. Okay. So like say we had, oh, let's play around with some functions. So we're going to say y equals the cubed root of x, of x minus 3 plus 2, okay? Actually, we won't do the plus 2. We'll just do x minus 3, okay? Now, what I'm going to do to that is I'm going to put an absolute value around that. Is it differentiable at x equals 3? No. Why? The limit from the left would not equal the limit from the right. It causes a sharp point. Okay, so that's another example. But I mean, as you can see, absolute value has a lot to do with things like this, okay? Not saying that it always does, but a lot of times. Another example of one that is not an absolute value is y equals like okay, so that's an example of one that would not be an absolute value.
It would be like trying to think of it.
I guess my question would be
Mhm.
from both sides, just visually, it would appear that as, let's say on the right one where it approaches 3, as x approaches 3, it seems that from the left and right, they're both approaching the same number.
Okay, but the slopes
Right.
that they do it with are different.
Okay.
So let's hold on. You guys need another visual on this. I would draw it up on the board, except people in Zoom land wouldn't be able to see it. So, okay. So now I'm going to drag this along so you can see. See that we have a negative slope tangent line as x approaches -1, right? Okay. As we go from the right, positive slope tangent line as x approaches -1. Now do you see why the limit from the left and the limit from the right are not equal? Because it has to do with the slope of that tangent line. So if I took the limit from the left, I would get a negative value. If I took the limit from the right, I would get a positive value, because this limit is always based on slope. What I mean by that is, when we look at the definition, this is slope. Okay? Are we good with that?
So is it possible for them to be not differentiable if they're, let's say, both are negative or both are positive?
As long as they're approaching the same number.
So it would be like 2.
I can't think of an exact function that would describe what you're talking about, but it's very obvious when one is negative, when one is positive, it's not the same number. But it would still have to approach, the limits from the left and from the right would have to actually be the same value.
Let's say like,
Even if they were both negative but different negative numbers, that would not be good enough. Even if they were both positive but different positive numbers, not good enough. Okay.
So let's say there was like a parabola, and the point that we're looking at is like at the, it's like at the kind of the vertex of the base of the parabola, and you're approaching that value from the left and right. And since
Let me show you. Hold on.
x squared.
Yeah. Let's do it. Yeah. There we go.
So if, let's say, like wouldn't those both,
So, okay,
aren't the slopes
highly
both-
negative, not so negative, approaching what as we get closer and closer to 0? Approaching 0, right? And from the right, highly positive, approaching 0. Now, does that answer your question? So normally at the bottom of the smooth vertex, those slopes are approaching 0 on either side. So they are approaching the same number. That number is 0. And that's a very important concept for understanding that the minimum of a function has a derivative at that point of the minimum equal to 0, right? Conversely, the maximum would do the same thing. Does that make sense?
what is for cubic?
Okay. Here we have a maximum and a minimum. So here we've got a maximum, and see how at that maximum the derivative approaches 0, right? At the minimum, the derivative approaches 0. So wherever you have derivatives approaching 0, it's going to be equal to a maximum or a minimum. So yeah.
Isn't like one way to think about it is that the tangent line in a parabola is 0, the slope of it would be 0.
When the slope of the tangent line is equal to 0 at a particular point, meaning you've got this function, and when you plug in a certain number, you get 0.
And like in absolute value, if we were at that point, the slope would be, is it like infinity since it would be a vertical line, or is that not?
Well, that would be a derivative, wouldn't it?
Okay, that one with absolute value, with the sharpness, we get that on the definition of a limit. We cancel it on the definition of a limit. You could probably Well, you wouldn't find one function. You would find one function for one half, one function for the other half, right? And when you plug your value in, you're going to get different numbers, maybe. But regardless, it doesn't meet the definition of a limit because the limit from the left and the limit from the right have different slopes. Okay? So we kill it on definition alone. It doesn't even meet the point where we would get to substitute.
So if I'm like, just processing it correctly,
Mhm.
they're not differentiable, and it's usually in the case of one negative slope and the positive slope?
Mhm.
Okay.
And that's that whole pointy aspect, canceling differentiability. Okay. Where did we leave off? Okay, so a function that is not differentiable at a point, okay, at which its graph has a sharp, function that is not differentiable at a point at which its graph has a sharp turn or a vertical tangent line, okay? So if a function is differentiable at x equals c, then it will also be continuous at x equals c, okay? So if we differentiate, then it's continuous. Differentiability implies continuity, right? If it is not possible for a function to be continuous and not differentiable. Or sorry, it is possible for a function to be continuous and not differentiable, right? As in absolute value, as in some of these other things, okay? So continuity does not imply differentiability. See definition discussion on sharp points, okay? So very good questions tonight, guys. I just love it when I have a class that, you know, asks good questions and really digs into this stuff to help understand. It makes the class so much more fun to teach. Okay, so that is section 2.1. We are going to go on very briefly into 2.2 because I feel like we've covered a lot of it. We're going to go into the power rule. Okay. So the constant rule. Okay. So the derivative of a constant function is 0, right? Well, duh. Let's take a look at a constant function, right? Just a new blank graph. Y equals 3. What's the slope of that line? 0. What's the derivative of that line? 0, because we're talking instantaneous rate of change, and that's slope, right? So along the whole function, it's 0, right? Yeah. So if I take the derivative of a constant, it is 0. Why? Because a constant is a horizontal line, and the slope of a horizontal line is 0, and derivative is slope. And they give you a handy-dandy little proof on page 110. So it does not depend on how we define these constants or what they look like. See, constants can look like a bunch of different things. They can look like y equals 7. They can look like f of x equals 0. They can look like s of t equals -3. They can look like y equals k pi squared, where k is a constant. Because pi is a constant also, isn't it?
Anything equals a constant.
Right.
The derivative is 0. Right.
It doesn't matter how many letters they are, right? You can have letters that are not variables. Are we good with that? That is why we have f of x, to tell you which one of all the letters in that mishmash is the variable, right? So if I wrote f of x equals k pi squared, that is a constant because there is no x in there. Because I said my variable is x. Do I see an x here? No, it's a constant. I know, we even did Pascal's triangle. Okay, so they show you Pascal's triangle here. That's why I wove it in where it just kind of made more sense to me. So They expanded it. We showed you Pascal's triangle. And that is the mathese for how to expand binomials. I think my way was a little nicer. But for those of you going on to higher mathematics, like discrete structures, you might need to decipher that lingo. So the power rule, if that's after Calc 2 and Calc 3 and differential equations. Then we have discrete.
Yes, but yeah.
However, you can take linear algebra at any point. So if you need a good course, except for eigenvalues and eigenvectors, linear algebra is the bomb.
Do you teach Calc 2?
I've taught it once. That's it.
You not like it?
I just have never had the opportunity to teach it again. Not that I didn't like it, it's just, I teach what they tell me to teach, but I don't ask for it either. Not that I wouldn't teach it if they really needed me to, but there's a certain group of teachers who really enjoy teaching certain subjects.
Yeah, you still do it.
And I let them do what they want. I used to be in the thing where they were like, oh, can you teach calc with apps? I'm like, okay, fine, I'll teach calc with apps. I dearly love teaching calculus, period, so I'll teach it however I can. But calc with apps is like calc without trig. So it's calc for non-tech majors, which as a teacher has a different set of challenges. Let's just put it that way.
That du over dx, that's just another.
That's
notation.
taking the
Okay.
derivative, yeah. That's one of your derivative notation. So we're taking the derivative of x to some power, right? And that's going to equal the power times x to one less of a power, right? N minus 1 is 1 less than n, right? So if I have f of x equals x to the 5th, then f prime of x equals x to the 4th. If I have f of x equals the cubed root of x squared, that is equal to x to the 2/3 power root, okay? Therefore, f prime of x equals 1/3, right? 2 minus 3 is -1, right?
Oh, okay.
We're subtracting 3/3, okay? And so that would look like 2 on top, 3 on the bottom. This is on the bottom because it's negative, cube root of x. See how I'm weaving all this in here? Because I know you guys don't like it. So if f of x is equal to 2 over the square root of x cubed, that is 2 times x to the -3/2. Negative because the x is on the bottom, 3/2 because 3 is the power, 2 is the root. Okay? So then f prime of x is equal to that number times, see, I extended a little bit, times x to the, we keep subtracting. So -3/2 minus another 2/2, right? -5/2. So this becomes -3x to the -5/2. Whoo, yay algebra. Okay, this is why I don't understand why we do radical notation.
Wait, so why do we have the -3 there from the 2?
because 2 times -3/2 is -3.
Okay.
-3/2 minus 2/2 is -5/2. We have to subtract 1. When we're subtracting 1 with the denominator of 2, it's -2/2. Okay. Okay. So, yay algebra.
This is so much easier than
Fractions are your friends. Okay? Yes, they are.
so much easier than what we would have.
Okay. So, we've done some of that. We've done some of that. Constant multiple rule. So, what we showed with that last problem is if I have a constant times the derivative of a function, it's just equal to the constant, or the derivative of a constant times a function is the constant times the derivative of the function, right? So, like if I have f of x equals 2x squared, right? Then f prime of x is equal to 2 times, what's the derivative of x squared? 2x, right? So that becomes 4x, right? So if I have f of x equals 3 times x squared, no, it's just, I'm just making these up. That equals 3 times x to the 4th power, then f prime of x would be, very good. So if I have f of x equals 3 times the square root of x, so this is 3 times x to the 1/2, right? Then f prime of x will equal, what's 1/2 times 3? 3/2. Don't think decimals, think fractions. X to the -1/2. So this becomes 3 on top, 2 on the bottom, right? And square root of x. Okay. Here's some other examples. Yes, so these functions right here are the functions that give you the ability to calculate slope at any value of x. So for 2x squared, when x is 1, the slope of the tangent line to the curve is 4 times 1, which is 4. Make sense?
So is that what makes it like calculating limits with this really easy?
Yes.
So when we have the derivative, the equation for it, we don't need to rationalize the denominator, right? I think it was mentioned earlier. But
No, please don't rationalize denominators. Just leave them as they are. I mean, convert back to radical form because that's the pretty form everybody's eyes are used to. But if it were up to me, radicals wouldn't exist. We would just deal with rational exponents. Make it simple. Because we convert back and forth so much in this course.
Can you just quickly
Go over what again?
just any of those? I don't
Okay.
understand where.
Okay, so what's the derivative of x to the 4th? Bring the 4 down, have an x, what's 1 less than that? 3. And then 3 times that gives you the 12. Okay? So what in essence you can do is just take the 4 times the 3, that gives you a 12, and then subtract 1.
Because they were basically doing the power rule times.
The constant. Yeah. Top number times left number gives you new left number. Subtract 1 from the top. If that makes sense. Okay.
So if we're doing that, we don't have to do the
On the ones that it says you have to, you have to.
Okay, in a perfect world.
I will torture you on food a little bit. Okay, sum and difference rules. Say you've got polynomials with lots of different terms. Guess what? You can take the derivative of each term and then you're Gucci. You're golden, right? Okay. Here we go. So the derivative of x cubed minus 4x plus 5. You find the derivative of x cubed, 3x squared, right? Find the derivative of negative 4x, which is negative 4. Find the derivative of 5, that's 0.
Wow.
Easy peasy lemon squeezy.
Okay.
That's sum and difference rules. Okay, now I am done. Okay?
I'm watching all of this on Cross Saturday tonight.
Was that all of 2-2 right there?
No,
No.
Oh, okay.
this was all of 2-2